My name is Joseph Espinoza, and this review video is about Jordan canonical form. This can be quite a difficult topic at first, and there are a lot of technical working parts involved in this topic. I think it's best just to do a quick video summarizing some of the key ideas about Jordan canonical form and to go over a couple of concrete examples as well. One of the working parts of Jordan canonical form are Jordan blocks. If we let T be a linear operator on a vector space V over an algebraically closed field F, for example, the complex numbers, this is important because we really need our characteristic polynomial to split for this to be valid. If this operator has a eigenvalue lambda sub I that has multiplicity k, and we let n go from 1 up to the multiplicity, then the Jordan block associated with this eigenvalue is the n by n matrix J sub lambda I. The characteristic polynomial of this matrix is just x minus lambda sub I to the power of n. And the single eigenvalue is lambda sub I. And its eigenspace is spanned by the column vector with n entries, where the first entry is 1 and the rest are 0. By doing this, we are constructing the following matrix. The matrix J sub lambda I is just the matrix that has as its diagonal entries the eigenvalue, and on the off diagonal, 1s. The rest are 0s. Before we start talking about the Jordan form for a linear operator, we should be certain it exists in the first place. Corollary 1 provides such a condition. It tells us that if T is a linear operator on a finite dimensional vector space V, whose characteristic polynomial splits, we can be guaranteed this if our field is algebraically closed. Then T has a Jordan canonical form. And it's defined as following. If we let beta be an ordered basis for our linear operator T that has k eigenvalues that don't need to be distinct, we'll see later, such that the matrix representation of T with the ordered basis beta is just the matrix that has as its diagonals the Jordan blocks that correspond to the eigenvalues of T. In this case, we call beta a Jordan canonical basis, and we call the matrix representation of T with this ordered basis the Jordan canonical form for T. Now let's take a look at a family of examples. If we let A be an arbitrary 3x3 matrix with entries from an algebraically closed field F such that it has 3 eigenvalues, then we're going to encounter 3 cases. The first case is familiar, and it's one that we like, and it's when all of the eigenvalues are distinct. Then we know A is diagonalizable. And the Jordan canonical form is actually just the diagonal matrix that has as its entries the eigenvalues of A. If only 2 eigenvalues are distinct, one will have multiplicity 2, and its Jordan block will be of size 2, and the other will have multiplicity 1. We can see then we're forced to have only 2 possible Jordan canonical forms. Of course, this is modulo the permutation of the Jordan blocks. And they look like this, where in this case, lambda sub 1 has multiplicity 2, and in this case, lambda sub 2 has multiplicity 2. If there's only one eigenvalue repeated 3 times, then the Jordan canonical form is just that Jordan block. So one of the reasons that we like diagonalizable matrices is that they sort of give us a family of similar matrices. That is, if 2 matrices are similar to the same unique diagonal matrix up to an ordering of their eigenvalues, then they're actually similar to each other. Let's look at an example. For instance, the matrix 0, 3, 2, 1 has eigenvalues -2 and 3, which are distinct, so we know it to be diagonalizable. In other words, it's similar to the diagonal matrix with its eigenvalues as the diagonal entries, -2, 0, 0, 3. But in fact, all 2x2 matrices that have these eigenvalues and same determinant are similar to this matrix. That is, there is a family of matrices that have as its nicest representative the diagonal matrix with its eigenvalues. But what about non-trivial matrices? In other words, besides diagonalizable matrices and the identity matrix and the zero matrix, do other matrices have families, or are they kind of off on their own? And regardless of not if they have families, is there at least some way to make them look nice, almost diagonal? Maybe we want them to look nice so they can find a family. Over an algebraically closed field, though, actually, this is true. All non-trivial matrices have families, and we can make them all look relatively nice, even if we have non-distinct eigenvalues. Let's look at an example. So I've already told you that the identity matrix, I told you that it was trivial, but I didn't tell you that it doesn't have a family. That's because the identity matrix and the zero matrix have to be unique. But this is sort of besides the point. The fact is that we have two 2x2 matrices that have the same eigenvalues and the same determinant. And according to the example we saw previously, you might intuitively think that they're similar. But we should be careful, because we should see that because the eigenvalues are not distinct, that the matrix 1, 1, 0, 1 is not diagonalizable. So there's going to be no way that it's similar to a diagonal matrix. But if we take this matrix, 1, 0, 1, 1, by the previous example on the previous slide, we saw that we sort of have to have the Jordan canonical form that looks like this. But just because this matrix has this Jordan canonical form, does that mean they're similar? So it does turn out that actually they are similar. But we've already seen that an operator in an algebraically closed field will have a Jordan canonical form. But is every matrix similar to a Jordan canonical form? First, we should define the Jordan canonical form for a square matrix A. And it's actually just the Jordan canonical form of the linear operator, LA. Corollary 2 tells us that if A is an n by n matrix whose characteristic polynomial splits, or in other words, its entries are from an algebraically closed field, then A has a Jordan canonical form called J, and A is similar to J. So we can check off the existence and the similarity for the Jordan canonical form of a matrix. But we also know that families of similar diagonalizable matrices are similar to a unique diagonal matrix. So is there some unique representative for these families of Jordan canonical forms? And this corollary tells us that we do. The Jordan canonical form of a linear operator or a matrix is unique up to the ordering of the eigenvalues. So we also know that the Jordan canonical form is unique. So far, so good. We know that the Jordan canonical form exists. We know that matrices are similar to their Jordan canonical form. And we know that it's a unique Jordan canonical form. So far, we're sounding like as close as we can get to diagonalizability as possible. We also just have to make sure that we have an actual family of matrices. What I mean by that is that we should check to see if matrices that are similar to the same Jordan canonical form are also similar to each other. And we should also be curious about whether or not a matrix can be similar to a matrix that doesn't have the same Jordan canonical form. And theorem 7.11 is going to cover that for us. It tells us that if we let A and B be an n by n matrices, each having a Jordan canonical form, then A and B are similar if and only if they have the same Jordan canonical form, up to an ordering of their eigenvalues, of course. So that means we can assume that a lot of things about two different matrices might be similar, or that they might have in common, right? They might have the same number of eigenvalues or eigenvectors, the same determinant, the same trace, whatever. But if their Jordan forms are different, that is, their Jordan blocks are of different sizes, then they can't be similar. For example, if we let these three matrices exist, they look quite similar, right? In fact, they each have the same eigenvalues with the same multiplicity, and they have the same determinant. Is that good enough for similarity? Well, we need to check the Jordan blocks, right? If we look at A, we see that there is a 3 by 3 Jordan block and a 1 by 1 Jordan block. If we look at B, we have one 2 by 2 Jordan block, a single Jordan block, and a single Jordan block, and again, a 2 by 2 Jordan block and 2 single Jordan blocks. So it turns out that because A has Jordan blocks of a different size, it's not similar to B and C, which are in fact similar to each other. In fact, C is just the Jordan canonical form for B. So now we're probably wondering how we even find the Jordan canonical form for a matrix. Well, we should recall our technique for diagonalization. We take advantage of the fact that A is similar to a diagonal matrix, and so we set up this equation. Here, the P matrices are matrices that consist of eigenvectors of A. The trick for Jordan canonical form is actually very similar. We set up the equation J is equal to inverse Q, B, Q. And the Q matrices here are matrices consisting of generalized eigenvectors, which is a very involved topic in its own, and it's best to watch one of the other review videos for that. This is the end of my presentation. Thank you for watching. Good luck on the exam, everyone.